Oh, thanks, Tony. It's 11 o'clock over here, and I want to give like a proper introduction to Cecilia, so I'll start right on time. It is my great pleasure to introduce Cecilia Mateu, Carnegie Colloquium speaker today, who is visiting us from Universidad de la República in Montevideo in Uruguay. So Cecilia is here for the week as one of the organizers of the Streams 22 meeting. Which is a workshop aimed at, well, many of you are participating in, but for people from Carnegie who are not, it's a workshop to get together and assemble a catalog of member stars of stellar streams in the sky. And so to borrow from John's welcome address yesterday for the meeting, he said that this is, like Carnegie has a long history of studying the structure of the Milky Way, and people like back in the day, in the very earliest days, like could not even imagine the kind of work that we are doing. And I think this is literally true because we're not even sure what the nature of galaxies or these nebulae were, let alone that they could be tidally dissolving, and which is what we are trying to keep track of this week, and I guess in our work more generally. But the reason why I'm starting this introduction for Cecilia in this way is because in some ways, or many ways, it seems like the times are like pretty similar in the back in the day where people weren't sure kind of what these nebulae were. They were pretty excited about them. They look pretty cool. And I think we're in a similar stage now with stellar streams that we are not really sure what they are telling us, but we are sure that there will be a lot that they can tell us. So this is why we are kind of gathering here today. And Cecilia is really continuing the grand tradition of astronomers in the Carnegie's past in this endeavor. So much like many people here at Carnegie, she started as a variable star expert. So her thesis from Venezuela was on the R-Lyrae stars and the structure of the thick disk in R-Lyrae. And then in a similar manner, kind of progressing further, wanted to ask kind of what the physics is and starting to realize that Gaia will play a very important role and start to think of how can we detect more stellar streams using more automated ways of finding them. That kind of fast forwarded to like just this year, where I think in the true tradition of astronomies of all, Cecilia had a single author paper. So that's not, a drawback, I know what is. And on this giant piece of work of trying to systematize all of what we know about stellar streams in one single reference. So this, I think, will be the main topic of the talk today. So I'll leave it to Cecilia and look forward to hearing kind of where we are and hopefully where we go in the future. So please take it away.
Thank you, Anna, for the invitation and for such a wonderful introduction. So, yes, I am on. Yes, one is on here. Thanks. So I'm going to delve right in after that introduction. So the title of my talk is Keeping Track of the Galactic System of Stellar Streams. And I wanted to start with this plot with not much explanation, just to say that this is how messy and amazing the halo of the Milky Way is looking at right now. It's looking like right now if you look at it on stellar streams. We're 100 years from knowing what a galaxy is, and now we have 100 things lying around in the halo, so, or nearly so. So what I'm going to be talking about is this effort that I've been leading in trying to, keep track of all these things that are mostly in the halo and what the information available is and what we can do with them. So our fellow Streams 22 participants here are going to forgive me for the next slide, which can be a very hot topic of debate. What is a stellar stream? So just a very broad definition that I wanted to give is that a stellar or tidal stream, which is how sometimes they're also called, is formed when a dwarf galaxy or a globular cluster orbiting a more massive host gets disrupted and starts losing stars due to the tidal forces that more massive host is exerting on the dwarf galaxy or the globular cluster. And that strips it not only of its stars, but also of its dark matter that even starts happening before the stars start coming out, if the system has dark matter, of course. So the thing with stellar streams is that, well, all the stars are going to be turned out, and eventually the stream is going to phase mix, and all the stars are going to incorporate in what we know and like as the smooth galaxy field components. So the smooth halo, the inner halo, the thick disk, or whatever. So the other important point here is that this phase mixing occurs over a long time scale in the halo. So this is where streams are long-lived, and where we can, the reason why we can see them and find them today, and they can live there or be preserved for several gigayears or even tens of gigayears. So the halo is the best place, at least up to now, to find, to search for stellar streams with, and that's why I'm always referring to streams in the halo. Of course, some of the people here are wanting to push that further and try to find this kind of structures in the plane of the disk, which is much more complicated. But so this is the reason why we're looking for stellar streams in the halo. And of course, you'll have different types of streams, and you'll have streams with more contrast if they're more dynamically cold because they have lower velocity dispersion, if they were produced by globular clusters, for example, as opposed to dwarf galaxy streams that are going to be more fluffy and are going to have less contrast with respect to the background, but that presumably could be more massive if the dwarf galaxy was indeed more massive. And of course, differences on whether the system has dark matter or not. So the other question that I wanted to start with is, why study stellar streams? Other than having the chance of simulating them and producing animations and things like that, which no one can resist, and the allure of trying to find and discover stellar streams, which many of us, of course, are also seduced by. So setting those two aside, coming from a place in Venezuela where we were very focused on stellar populations, the way I see it is that stellar streams are to dynamics as stellar clusters are to stellar populations. So relatively simple, with many quotes, relatively simple systems of stars that have a common origin, and therefore they have a common set of properties. In the case of clusters, those same properties would be the distance, the age, the metal abundances. Again, you put quotes on all of that. You know the caveats and the nuances there are to that. But that makes a cluster stand out much more clearly in the field with respect to the field. So this is just a color magnitude diagram of the PAL5 cluster from some spectacular data that Anna Bonazza has taken for the PAL5 cluster and later the stream as well. So you can see how the cluster delineates an isochrone, and you can really tell it apart from the field very easily. So in the case of streams, the same properties are no longer these. They are, for example, integrals of motion. So they have the same energy, the same components of some angular momentum with respect to an axis of symmetry of the potential. So if you now plot in a different space, so integrals of motion space, then you have the background in gray, and streams are very well localized in that plane. So this would be one of the ways of picking out stellar streams against a background, or trying to link different streams together because of shared properties they have in this space. So the idea is that these common traits or properties can be used to find these the clusters or the streams because they stand out against the background, but also to be able to model them will help us infer properties about their own origin and about the background itself, because you have to know how the two work together, how the two interplay. So to push this analogy further, stars in a stellar stream they're spread out, not in any way, but approximately, again, quotes, delineating an orbit, similarly to how stars in a cluster delineate an isochron in the color magnitude diagram. So they're telling you where the orbit is, which is something that on a human timescale we are never able to see in any other way. So you're basically getting all the breadcrumbs of the progenitor that it's telling you where the orbit is or is going to be. So this is the example of the discovery paper for the PAL5 tails. So the cluster is way up there in the middle, and these are different orbital fittings. So of course, how the stars distribute along the stream is going to depend on many things. But the idea is that through some very complicated form of orbital fitting, you can, if you know what the potential is that is causing the stream, then you can predict, given the velocities and the positions and so on, then you can predict the orbit. So you can turn the problem around and do inference of what does the Milky Way potential have to be so that you can observe, you can produce the stream that you are observing and have the velocities and the positions and everything, the distances that you have. So that inference will provide us with the shape of the potential, and also that's related via Poisson's equation with the mass distribution, of course, mainly dominated by dark matter, and also the total mass enclosed by the stream in its orbit. So that also that relates to the galaxy that's doing the tidal stripping, but then there are also other internal factors to the progenitor of the stream and the rest of the environment the stream lives in. So modeling not just the orbit, but the substructure along the orbit, the density profile along the stream, the perturbations, gaps, spurs, cocoons, and all kinds of crazy things that people are no longer speculating about, but actually observing. And please, all the experts here, forgive me for only picking a few examples. This is an example of GD1, where Anna and Adrian Price-Wayland observed for the first time these gaps, presumably due to interactions with dark matter subhalos and features like spurs, and then Kiati Malhan observed something like a cocoon, and things can get very complicated. So the idea is that by modeling all of these things, you can infer things about what was the progenitors, the stream progenitors' initial mass and configuration, and also try to put constraints on the mass distribution of dark matter subhalos or other perturbers that might be responsible for causing these gaps and these breaches and things like that. So, of course, if you only do this with one stream, this problem is highly degenerate. So, because I'm telling you that all of these things are interplaying and intermixing here and producing just one set of observables. So ideally, you would want to break that degeneracy by fitting and studying multiple streams. And this has only been possible in the latest years, as we will see now. So this is from the dynamical standpoint, but then there's sort of an immediate thing that you would want to do with streams, and that they are obviously, especially if they're dwarf galaxy streams, a fossil record, a clear remnant of the accretion process. So you would just like to do a census, just count, measure, do all your dynamical modeling, measure the mass of each stream, and then just assemble that in what we like to call the accretion history. So if you ask a stream expert, they're going to tell you, we want to figure out what the accretion history of the Milky Way is. And that we're envisioning that is going to look something like a plot with mass as a function of a time coordinate. So look back time or in-full redshift or whatever you like, where you can know how much mass was accreted at a given time in how many building blocks. And from that, construct a merger tree that you can compare to cosmological simulations, for example. The thing is that this all sounds very nice, but stellar streams are not the only fossil record or the only remnants that are produced by the accretion process. So, so they're part, but not the whole of the accretion history. So I'm borrowing here some observations of streams observed in external galaxies. So streams are very coherent features in configuration space, but also there are other products, depending on the type of orbit the progenitor has, that can look more like a cloud. So something that we call either a cloud or an overdensity, or sometimes a shell, when a very radial orbit produces something that looks like an umbrella. So it has a very coherent part and then a very fanned out part. So these things are detected in ways that are different from the ones that streams are detected with. So there are overdensities. Many of these are known, observed in the Milky Way. So early ones are the Hercules Aquila, and so this is Rocha Pinto and so on, 2001. The Virgo overdensity, which now has a new name, the Virgo radial merger, I think, and a couple other more. So I think these are the biggest ones. But then things can actually, and will eventually, be completely phase mixed. So the earlier and the more massive events that have already phase mixed have also, many of them, been identified in the Milky Way. And I think the most prominent example is Gaia Enceladus, or GES, which stands for the Gaia Enceladus sausage. You can ask me about that later. And where things are just spread out entirely around the sky, and you notice that these mergers happened by looking at kinematic signatures, like a very radially asymmetric distribution of the velocities for a set of stars, or looking at other things that I'll mention now. So many of these phase mixed, no longer coherent events have also been identified in the Milky Way, and they are a very big part, especially in mass, of the accretion history. So rebuilding the accretion history means that we actually have to look at all these things together, right? So as a full picture. So just to give you a bit of an example, I wanted to touch on how much of the accretion history can we then expect to recover from tidal streams. So this is a plot from a study that I was doing with the automated method to recover tidal streams. And this was using mock catalogs to simulate what Gaia would observe if the Milky Way were like one of these galaxies from the Aquarius simulations. And the idea is that each dot here is a progenitor, or potential, it's a building block of what results in the Milky Way. And you have here in full time, so when the building block was accreted, and this is heliocentric distance, so very observable quantity. And the colored dots are the streams that we were able to recover with our method. But the important thing here is that you can see a very clear correlation, and these bars here, which are not error bars, they're telling you basically how disrupted the progenitor is. So all of these things that are falling in right now basically are completely bound, and they haven't had any time to disrupt. So these are things that still survive as bound galaxies or globular clusters, or galaxies in this case, because these simulations did not have the capacity to self-consistently produce the formation of globular clusters. But then as you go further back, things have had more time to interact with the Milky Way to come closer and start losing stars. So the regime where streams are produced is over here, and then things that were accreted a long time ago and that have come very close are just too disrupted. So these things would be sort of the Gaia Enceladus, this Thamnos, Sequoia, and so on that I mentioned before. These are, like I said, surviving dwarfs or globular clusters. And then there's something in the middle, which are our streams, and of course the clouds, depending on the morphology. So with stellar streams, we're probing this range here in, if you like, accretion redshift, and also in distances. So you can't really probe the very outer halo with stellar streams because things are not going to have lost stars and disrupted yet. And something similar happens to masses, of course. And of course, you now also have to convolve all of this with all our biases in our observations and our detection techniques. So we have to keep all of that in mind. But like I mentioned before, I think it's the easiest to think that you can just look at the stellar stream and fit the orbit and get the mass. And if that is a stellar stream that was produced by a dwarf, then great, you put it in your plot and you have your little building block. But most of the streams we know of in the Milky Way, and when I say most, is like the absolute vast majority, so like 90% almost even, are stellar streams that have been produced by globular clusters. So, I mean, by mass, they don't really count, they don't really contribute that much directly to this plot that we're trying to reconstruct. So you have to get a bit more clever, but it's not, of course, they're extremely useful in all of these dynamical applications that I mentioned before. But actually, they do count for the accretion history because, as extragalactic people know, the systems of globular clusters are very good tracers of the masses of their host galaxies. They're very well correlated. So if you look at globular cluster groups or globular cluster sets that have common sets of properties, this is metallicity and age, you see these sort of tracks in this plane that can allow you to identify clusters that probably fell in together and then tie that back to what the mass of the host galaxy was. So the idea is that this was done with globular clusters that are not disrupted. So now we would have to link that and fill back in, well, these are not all the globular clusters that presumably that original galaxy had, because some were probably disrupted and left their tidal stream somewhere. So we really have to connect the bound globular clusters to the streams that were produced by globular clusters. So also find a way to link those accretion events to the streams that we have discovered here in the Milky Way. So going back to this plot again from Anna, you can find overdensities and in this plot and link together which streams probably were created in the same event, and then try to link that back to what you know from the globular clusters and other methods, of course. So so basically, streams, either if they were produced either by globular clusters or by dwarfs, they are very useful in reconstructing the accretion history. That's a basic message of this part. So now the thing is that we have to know what it is that we have so that we can start counting and start pulling this together. And of course, in order to be able to reconstruct that accretion history, we're going to have to see what the effect is of our selection function and try to model some kind of completeness, which is absolutely something that we are all very keen on doing and that we're not going to be doing this week, because we have to be doing something even more basic, which is to figure out what it is that we have and make it consistent so that we can now start trying to do more fancy things with it. So just know what streams we know, what do we know for each, and how much of these all super interesting analysis we can do, and whether we have the information to do them. And if the information can be used together. So this is another look, but more observational one of the first plot that I showed you. This is the sky plot in galactic coordinates for all the nearly 100 streams that we know of in the Milky Way from the plot that Anna mentioned in the introduction. So each line you see here is a stream, and all the stream experts right now are looking for their favorite stream, probably. So right off the bat, note that this is the galactic plane, and there's a big hole there, which is a big observational bias that it's extremely difficult to pick something so faint out of in such an immense background. So how did we get to this? So it all started in 1996 when a couple years prior, the Sagittarius dwarf was found by Rodrigo Ibata, and then the first tidal tail was discovered. And a few years later, it was traced using 2MASS, about in 2003, by Steve Majewski. So that was the first all-sky view of the Sagittarius tidal stream. So it was all very quiet at first, and then we started getting some bursts, and now it's just growing very fast. So very, very quickly, and please feel free to ask me about this later. What are all these peaks and things attributed to? So up to Gaia DR2 was the reign of the photometric methods to find stellar streams. Mainly matched filter, which has been, and I think we all know that it's going to continue to be a very prolific method to find stellar streams. So this bit here was the reign of SDSF, and I remembered not to call these Karl's streams, which at some point they were named that in my in my talk. So this was the years where you would see many papers from Karl Grillmeyer on the first tidal stream. So after Sagittarius came PAL 5, and then, okay, I just forgot which one this is. I had it there somewhere, but Orphan, the anti-center stream, the GD1, which is of course everyone's favorite, NGC 5466, and so on. And I tried to fit the references here. I put them at the end. And then, okay, so more matched filtering was able to produce some more streams, and there were some scattered other discoveries, a couple from radial velocities, notably the 300S stream. So I don't know if Josh is in the audience right now, but this one was discovered by radial velocities, and if I remember correctly, also the parallel and the perpendicular streams. And then came PS1 and DES, also using very fancy techniques of matched filter. And with DES, the southern part, the southern hemisphere, the southern galactic hemisphere started to get streams, because with SDSS up to about here, we were only finding streams in the northern hemisphere. And I found a couple of candidates with RLR that I'm very keen on seeing if they will survive the test of streams 22 and will be able to find the associated population. But then after Gaia DR2, then came the reign of the proper motion or the kinematic methods. So the methods that use kinematics and fold in orbital predictions or dynamical information in some way. So you can see that the number after 2016 increased a lot, like by a factor of 5 or 6. So it just suddenly exploded. And that's why keeping track of all of this is getting more and more complicated, but also important. So the information is just scattered across the literature. So to borrow the term from Alex, who said it yesterday, it's the wild, wild west. So things are reported in a very organic way. So very differently, which makes collating all of this take some time. So you can, for example, get in a paper endpoints for a stream that is relatively short, which is good, or a pole, like in this case. These are from Edouard Bernard's PS1 streams in 2016, or maybe a track or just an indication on a plot. So this was not the case, but I just wanted to show you a typical thing of course, you can clearly see here the Segway 1 stream, and that is obviously visible in this image. So to a trained eye, it's perhaps obvious. it's visible, maybe not even to a trained eye, it's obvious. Then at some point, people started reporting polynomial fits in their whatever celestial coordinates they had, and more recently, lists of member stars with membership probabilities. So it was becoming necessary to do a compilation of all of this, inspired following this historical introduction that we were making, inspired by the many useful compilations that we've all had the pleasure to use from the past, like the Harris catalog of globular cluster, the McConaughey catalog on dwarf galaxy, and the Clement catalog on variable stars and globular clusters. So that was the inspiration for all this. And the idea was that this would report just the tracks. It started with just where the track is in the sky, that was V0. And after we started getting kinematic data, that's what's in this year's paper, also the tracks in proper motion and so on. And the idea was always to provide the starting point for what we're doing now. So in streams 22, so just know where to look, where a stream is supposed to be, at what distance it is, and so on. So the information that's encoded on Gauss streams is the basic unit is a track, which is a property as a function of an angle. So that property can be many things. Right now, the properties are just the other angle, so that's the celestial track, so you know where the track is in the sky. The distance as a function of, again, an angle, the proper motion, and if there's any information available in the literature, radial velocity. So the idea is that a track on Gauss streams may look somewhat like this. This is, for example, the Phoenix stream in galactic coordinates. So this is L and B, and this is a relatively short stream, and you have, well, not much of a distance gradient that we probably want to remeasure or measure for this, and proper motions there. And the idea was to put all of this in a Python package that would use all the functionality from AstroPy, so that you could do coordinate transformations transparently using all the wonderful tools they have there. And there are also other attributes that I'm not going to get into, but you can ask me at the end if you'd like to know, pre-computed for each of the tracks. The most important one, I would say, is the stream's coordinate frame. So the new rotated coordinate frame in which the stream lies approximately on the midplane, which makes everything easier, and around the coordinate 0, so that you don't get something, the problems you have with the cyclic coordinates. So you can transform to this phi1, phi2, which is the standard nomenclature for this. And everything is supposed to look simpler in that reference system. So this is the same stream, but now in phi1, phi2 coordinates. So you can use this to compare different tracks in the literature that are tracked in there. So I said there are close to 100 streams, so formally 97 streams, but there are 125 tracks because different authors have looked at the same stream in many instances. So for example, you have here BAL5, where Nate Starkman found an extension on the leading tail of BAL5, but then you have issues like, for example, that track, which is the light purple one, doesn't have proper motion information, which is available on the other two, and that sort of thing. And also to try and figure out which streams that we thought are different actually are linked. So this was already known. It's not that I found this with by doing Gauss streams. This was already known, but you can see it here. So that the Giol, whatever, I don't know how it's pronounced, stream is linked. It's a bit of the NGC 3201 stream. And then you can also have a look at things like the M68 Fjorm stream that we are looking at this week, which Palau figured out it's the stream from M68, but it's also what Ibata had found and named as Fjorm. But then also in Ibata's paper, there was something called the M68 stream, which is this orange track here. But if you look at it in proper motion, it's nowhere near this other thing. So this one, we should probably rename something else and figure out what it is. So now trying to go back to the ensemble view of what's available on the library. This is a plot that I happen to like very much. I think this is my favorite plot from the paper because it showed something that was unexpected at first to me. And that is, the idea is to summarize here what things have been measured and what things are along the track and what things have been either assumed or just computed as a mean. So for most of the streams, we have the celestial track actually mapped in the sense that you have an empirical track that tells you where the stream is. And the assumed in this instance means that you only have the endpoints and you assume that's a great circle, which for a short stream, that's a good assumption. For a long stream, it's not. Case in point, I'm not showing it, 5466. If you do the great circle, it looks like this. And if you look at the actual track, it goes entirely through a different place. And that's a very long stream. So that happens sometimes. And then the distance point, which is my favorite point. And that is that nearly half the streams have only an average distance. So not a distance gradient, a distance measured along the track. And people who do dynamics are going to want that because things can go very wrong if you mess up the distance by that much, especially in a long stream. So something as basic as the distance, we don't really have measured in a consistent way for half of those 100 streams. And actually, the proportion is worse than for proper motions because Gaia is so cool and so many of the streams were discovered with Gaia that almost 2/3 of the streams do have a proper motion track, but they don't have a distance track. So standard candles to the rescue here, where they can. But this is one of the things that we are tackling this week. And of course, as you can imagine, radial velocities are much harder to get and also to track in the literature. So right now, only about 12% of the streams have radial velocity info, but actually the real number is larger because there's a lot of things published for like maybe 3 stars along a stream that are extremely hard to track in the literature. So have that disclaimer there. So getting into some more fun things that we can look at with just this, the available information. I'm showing you here what the discovery timeline looks when you fill. So the filled bins are the ones that have the information on the tidal. So the filled purple bins are, the streams as a function of time that have the full measured distance track, and the empty parts are the ones that lack it. So you can see the correlation with Gaia is strong, but even after Gaia, there are a few that are lacking information. But then here, I'm plotting this as a function of length, just to make the point that it's not only the short streams that lack distances. So we do have to do that homework. So some of the long streams are lacking distances. One other thing that we can look at are the distance biases and the distance distribution for the streams that do have empirical distances measured. So if you uniformly populate a stream track and then just plot that in a distance histogram for all the streams, you get something like this. So the gray line is when you do it for the 100 streams altogether. And then the colored ones are showing you streams detected by groups that are prototypical of a given technique. So the DES streams and pre-Gaia DR2, these are Carl's streams, basically. These are the matched filter ones, so the photometric streams. And these are the stream finder streams. So as prototypes of the kinematic and orbital fitting detections. So you can see that these distributions are entirely different. So and that's definitely an observation of bias. It doesn't require much of an sophisticated analysis to reach that conclusion. But the idea is basically that photometric methods are better at detecting things that are at greater distances, because that means smaller angular size and higher contrast against the background. So things are easier to find when they're actually not so close. If you're, oh, sorry for the Spanish there. Okay, so that's meant to say just photometry, but you get the point. So that explains why this rises here. But then, as we saw earlier, you expect fewer streams as you go to larger distances. So that explains this decay here. So that's why the thing peaked. And this is the 20 kiloparsec peak we saw even on the first version of the galaxy, of the Gauss streams library that we discussed in a previous workshop. Why are all the streams at 20 kiloparsecs? Well, this is just to show that, I mean, the photometric ones are, and it's an observational bias. So photometric methods tend to detect streams in those distance ranges better. Okay, so this is all that I was just saying. And kinematic streams are more prone to detecting nearer streams, basically because they require proper motions with good uncertainties. So this is determined by how good the uncertainties on the proper motions are in the Gaia data release that you use to detect your streams. So that's why the kinematic ones are found at shorter distances. So there's a sweet spot here where we are probably going to detect many streams when we can push this further or figure out how to make a combination of these things. So perhaps that gap is going to go away or change when we take into account the observational biases there. So the other thing that's very close to my heart that you can do when you have a track that has a distance for a stream is to compute orbital pole tracks. And what that means is that you can just look at what the normal vector is for the stream at each point in the track. And if you do all of this in the galactic center, so you stand in the galactic center, you take a star in the stream, you take another one, you do the cross product, and you get a pole. And that tells you the plane where those two stars sit. So that should be parallel to the angular momentum if the stream was produced in a perfectly spherical potential, because in that case, the stream would be perfectly planar. Even if it's very complicated and has many wraps like the case that you're seeing up there. So this would be a pole count map. So you're counting, you're plotting the coordinates of each of the pole vectors and counting how many stars, how many pairs of stars have that pole vector. So the redder means more stars. So that's very localized. So that's telling you that that stream, that's very complicated, that sits on a plane. Now, if the potential is not spherical, then that gets messed up, or it's perturbed, then it gets messed up in different ways. So the signature in pole counts or in pole space gets spread out. So things get more complicated. So looking at the poles can be a surrogate for looking at the angular momentum without using velocities. So, because velocities are expensive and Gaia is amazing, but not perfect. So having celestial tracks, we can do this thing and compute the pole at different parts of the stream and create a pole track. And if the stream is not a great circle when you project it, all of these are seen from the galactic center, then the pole will change along the stream. So you won't have something like the upper case, you will have something like the lower case. And also that will happen if you had some sort of precession or perturbation, if precession can occur, for example, if the potential is slightly flattened. So this is what happens in Orphan. This is the pole track. This is not mine. This is from Sergei Kopasov's paper in 2019. So this is the pole track computed using our Lyra stars for the northern part of Orphan, all of this, and the southern part of Orphan. So first you can see that this is not a dot. So something's happening there. There was probably precession here. These are model predictions for flattened, perfectly spherical halo. So this is what it would be if it was perfectly spherical. And these are the tracks if the halo was a little bit flattened. So some of the orphan stream is telling you that there's precession, but the rest is telling you that something very funny is going on. So definitely not spherical there, or something happened. So pole tracks are a way, like I said before, of looking at the angular momentum without having not only radial velocities, but proper motions even, under very strict assumptions. So if you look at pole tracks in the sky, you can do interesting things. And some people have looked at clustering of globular poles for dwarf galaxies and globular clusters, and found that they tend to cluster around something called the vast polar structure or something like that. And so there's a preferential alignment there. So Alex Riley, who's also here, Riley and Strigari looked at this for stellar streams with the previous version on Gauss streams, and they also did some literature searching on their own, and they found that there was no preferential clustering for streams in pole space. The thing is now, this was computed using the endpoints, and the scatter you see there is representing uncertainty. But now with Gauss streams, we can actually do this for the pole tracks. So with that, assuming that the streams are well represented by the endpoints, which is not true for the longer streams. So this mess is what you get when you do it for all the streams. So some of this is observational biases, but this part here is showing there's no preferential clustering around the DPOS, but there might be some areas where there could be some clustering, but we have to look at the selection effects, because there are some parts of this diagram that are going to be less populated because we don't sit in the galactic center. So this is something else that we would like to have a look at. And the other funny thing that was happening with orphan, yes?
The last one. So what's the hypothesis for why those don't agree?
Well, one of the things is that maybe the existence of the vast polar structure is still under debate. So how much of this is an actual observational bias or not? So, and that you might be just tracking different things. So these things may have, some of these may have fallen in together, but not all of the streams need to have fallen in with the same event that created this. Yes. So to go on really fast onto orphan, and I have like 4 more minutes. I told you that there was a bit that looked like that could be precession, but the other thing was doing something funny. And this is also something that was in that paper by Sergey and a bunch of us, where the first evidence for proper motion misalignment was observed, that if you plot the stream, like I said before, the stars should be along, the stars in the stream should be along an orbit, and we've been taught that velocity is tangent to the orbit, so proper motion should be too. And turns out that in the southern part of the orphan stream, they're not. They're very not tangent to the stream, which was extremely exciting and surprising to see. And long story short, you can measure that misalignment by looking at the tangent to the track and the ratio of the proper motions in the 2 coordinates. And if these things don't agree, then something perturbed the stream. And what Denny Circle found then, and later Nora has also observed, Nora Ship, in some of the DES streams, is that this misalignment is due to recent interactions with the LMC that has basically kicked a part of the stream, and the velocities have moved. So what you're seeing is no longer the orbit that those stars are going to be following. So we can now look at this again with Gauss streams and compute the tangent tracks and the proper motion tracks. So the tangents are the gray lines and the proper motion tracks are the black lines. And if nothing is perturbed, if things are not perturbed, the lines coincide, like in these cases. But when they don't agree, then something probably happened there. So these are a couple that are, to my knowledge, not reported in the literature, and some that are, for example, from NORA. And I'm excluding here all the things that only have a mean proper motion or a mean distance, in which case you could be getting the misalignment because you're not really getting the actual distance that you should be using. So you could have like a celestial map of where are you seeing those misalignments. So the purple colors here are showing you where most of the misalignments are. This is orphan. And then there are all these other cool things. So it would be fun to explore if there are areas where there's more of this and it was caused by the same perturbation or not. And all the gray lines show you the potential for the things that we are going to measure this week. And there are regions where there are many streams, so it would be very interesting to see what happens with this proper motion misalignments in those areas where there's a big density of stellar streams. So just to wrap up with the last thing, I absolutely could not finish a talk and not mention something on RLR stars. And this is actually not related to anything that's on Gauss streams, but one of the things that I'm very keen on doing with Gauss streams is it's looking at the RLR population of all the stellar streams. When Adrian and I did this for PAL5, we obtained the distance and the proper motion tracks, and that's so great. But PAL5 is a global cluster that's very well known for having RLR stars of only one type in the cluster, which are type C stars. In this amplitude and period plot, type C RLR are shown here. These are first overtone pulsators. And these are the more famous and more widely used for galactic structure purposes, AB RLR. And so the cluster only has type Cs, but then when you look at the tails, it's full of type ABs and there's only 2 type Cs. So they're like segregated. So you don't have AB stars in the cluster and you basically don't have C stars in the tails. So whether this only happens in PAL5, we don't know because we haven't done this industrially for all the streams. But it would be very exciting, particularly because there are several globular clusters that are rich on our C stars that maybe we wouldn't have looked when searching for stellar streams. So this would be I'm very keen on looking at what's going to happen. It may just be that PAL5 is like that and that's it, but we don't know. So this would be very interesting to look at. And it's something that Bruno is going to be, who's also here, is going to be looking at in his master's thesis project. So just to recap a little bit, this week we're going to be doing some intensive work on Gauss streams. And the idea is that we're going to be filling in some gaps in the data and the knowledge that we have for stellar streams. And the idea is that we all go on then later to do all these fun things and many others that I didn't get a chance to mention. So I think I am done with this here. If you find a new stream, then I may miss it on the archive if I couldn't check it that day. So please write to me and tell me, and I'll try to put it on Gauss streams. And many thanks. So this is what we're planning on doing. Okay, and that's it. Many thanks for.
Thank you, Cecilia, for the wonderful talk. Anyone has any questions, please raise your hand. Okay, Tony.
So if we wanted to get more distances for the streams identified through the photometric surveys, what would be the best way to do that? Or, yeah.
Okay, so if the stream has any RLR, I think all the RLR experts would agree that's the best way. But the problem is that there are many streams that are not luminous or massive enough to have more than a couple or that maybe don't even have a single RLR. So in that case, main sequence fitting along the track is probably going to be the best. Also, something that we're exploring this week is using RGB stars as standard candles. We're never going to be as good as RLR, but if you don't have any, then that's one of the avenues we'll pursue.
Any explanations at all as to why there only are C's in the cluster and are B's at the tail? That is very strange.
That
I
is
think.
very strange. So the first thing I thought was, okay, so type C stars are slightly hotter than our type AB. And would think, okay, so that's correlated to mass. So maybe it's mass segregation. So Eduardo can tell you better than I can that in globular clusters, there's mass segregation of the stars. So the lower mass stars are stripped first and they go onto the tails first. And then it's only when the cluster is like finishing getting disrupted that the higher mass stars get stripped out. But then when you look at the masses of the type Cs and ABs, it's backwards. So we should have had ABs in the cluster and Cs in the tails, if I'm right. So because you would have to look at not the present day mass, but the mass they had when they were stripped, so the initial mass. So it's looking like that's not the way. So the honest answer is, if that's not the way, then I don't, right now I don't know. Because this is the only case that we have seen this in. And this is also, sorry, this is an important point. This is not an observational bias. We know the completeness of the RLR surveys along PAL5. So we know it's not that we're missing type C RLR along the track. We know how incomplete we are, and it's only about maybe 10 or 20%. So that can't explain the difference. And the completeness of the ABs is close to 100%. So that's not it. So it's not, in the case of PAL5, that's not an observational bias. So it would be really fun if we saw something, some other cluster that has the same effect.
Okay.
Thank you. Here.
Hi, thank you for the talk. I have two questions, but something related with what you have just answered. Regarding the fact that the last stars to be sent are the one of higher mass. For GD1, that we don't have the progenitor, is there any overdensity of higher mass stars in some place, or has that been looked for?
As far as I know, not. And I don't think mass segregation has been looked at along the stream. Yeah, that's the short answer.
Okay.
So I'm looking at the GD1 experts here, but that's, yeah. So
I think like in any stream that we really measured mass segregation, like even in PAL5, I think it's
Okay.
get down to the lowest mass stars to see the effect.
Yeah. So you have to go really deep to even possibly detect it. So that's the other thing.
Okay.
Yes.
And one question: after we finish the catalog for the 97 streams, are you planning to have a parallel track with the new tracks found from the cats, or will you keep both tracks, the originals and the new, or will you update cat streams?
This was one of the things that we were discussing yesterday on working group 1. How are we going to proceed once the tracks are updated? So the way I see it is that you don't overwrite anything ever. So this is version 1 of Gal streams. So we would presumably feed the new tracks into what would supersede this version, and it would be a new version of Gal streams, in which the documentation is going to be so much easier. But yes.
Well, and the second question, thanks, is that how have you computed the poles using only for streams where you have the three components of the angular momentum?
No. no. The idea is that you don't use the angular momentum.
Yes.
Well, I don't. So for pole tracks, you can do it if you have the proper motion and rate of velocity, then you go and compute the angular momentum. Yes. But for the pole tracks, what you do is that you go to the galactocentric reference frame, you have the track, and then imagine 2 points along the track. So you have 2 vectors, you do the cross product, and that gives you another vector, and that's the pole.
So you have made a differential computation.
Exactly.
Okay.
So you do little steps along the track
okay.
and do the pole on each step, and that's what you get on
Okay.
those.
Thank you very much.
Was there a question here or, okay, Tony, next is Danik.
So I just had a quick question online from Ian Thompson, and he just wanted to know, in the PAL5 sample, how many R Lyrae are there?
I should know that number, right? Let me have a look at the plot and I'll eyeball it, but it was like 20 something, 25 or yeah, members. Yes.
28 in the paper and 25 that is in the Gaia.
Okay, great. Thank you. Thank you, Zanik. Yes. 20 flights. Yeah, that was pre-pandemic. That was ages ago. Yeah, so it's
Great.
20 something.
Like for the people on Zoom, how many? I'm not sure they.
Okay. So 25, 28 in total, 25 are in Gaia. Yes.
All right, great, thank you.
Which is a very decent number. I mean, 25 RLRs is a lot. So, I mean, in RLR world. So.
Continuing in the pulsation spirit, you showed a global cluster M5 that it has it's a leading trailing arm. It's like M5 had a stream there, right? That was in one of the.
Was it in my? Yeah, this is one of Carl's new streams. Let me.
It was, I don't know, somewhere in the middle.
Wait, let me mirror the display because it's going to be easier for me to. Yes. Okay. Here.
Yeah, exactly.
I didn't realize I had M5 there. Yes.
This is just my feeling, but it has only one arm,
Uh-huh.
and it's a global cluster that has plenty of auroral stars. Have somebody
yes, exactly.
looked
That was
into
my
that?
thinking as well. That must be crawling with RLR
Exactly,
stars. That was
exactly.
my thinking. I don't know if you looked.
I
at
haven't
it,
checked it. I didn't even know that it's supposed to have
No,
a
because
stream.
Carl is sitting behind you.
What was the
So I'm
question?
looking at the owner of the tails.
I have not looked for R, Larry.
Okay, so
But yeah,
that was my thinking as well, because M5 has many RLR, so you would think the tails would be crawling with RLR, same as PAL5. So yes.
Okay, I think this is a good place to stop before we add more on your to-do list. So let's thank Cecilia again.
No problem. And I'm here for the rest of the week, so we can chat over coffee breaks or. Thank you.
Thank you all.